Alright, so in this video we're going to solve a related rates problem. So the problem reads, a spherical balloon is inflated with helium at the rate of 100 pi feet cubed per minute. How fast is the balloon's radius increasing at the instant the radius is 5 feet? Okay, so let's go through the problem and highlight what's important. So it's a spherical balloon, so we're dealing with a sphere. Alright, it's inflated with helium at the rate of 100 pi feet cubed per minute. Okay, so when you see the word rate, you want to think time. Rate is related with time. Okay, how fast is the balloon's radius increasing? Okay, so how fast is the balloon's radius increasing? Okay, so fast radius increasing, that tells you that you're going to be looking at the rate of change of the radius at the instant the radius is 5 feet. Okay, so I'm going to have this radius. Volume of a sphere is 4/3 pi times the radius cubed. Alright, and so what do we need to do here? We need to get an expression for the rate of change of the balloon's radius. Okay, so we need to have, we need to differentiate with respect to time, right? We need to get a dr dt. So first I'm going to write this as a function of time. So v of t is 4/3 pi r of t cubed, right? And now we want to take the derivative of both sides with respect to time, right? So d dt of v of t. Alright, these are constants, so they stay the same, 4/3 pi. Now we have the chain rule here because we have something cubed and the interior is a function. So first we take the derivative of the outside, which is something cubed. So that's the power rule. It's going to be 3. Leave this the same, and then squared, right? And then, to complete the chain rule, we multiply by the derivative of the inside. That's the derivative of r of t with respect to time. So that's dr dt. Right? And now I'm going to drop the of t's. I'm just going to rewrite this. So this is going to be dv dt. Same thing, right? So we've got a 3 here and a 3 here, so those are going to cancel. So we've got 4 pi. That's going to be r squared. And then this is going to stay the same, dr dt. Alright, and so let's see what we got here. So they gave us the rate that the balloon is increasing in volume. Alright, we know it's volume because it's feet cubed. Alright, so this is going to be dv dt. Alright, think about the units of dv dt. It would be feet cubed divided by minutes. So let's plug that in. So we have 100 pi feet cubed per minute. And we got 4 pi, those are constants. And then here we've got the instant the radius is 5 feet. So they're telling us the radius is 5 feet. So that's r, right? We just plug in 4r. We got 5 feet squared. And then dr dt. Well, they don't give us that. That's what they're asking for. How fast is the balloon's radius increasing? Rate of change of radius with respect to time. That's the unknown. Okay, so let's move up here. So let's look at both sides. Each side has a pi, so let's get rid of those. And then I'm going to divide both sides by 4 to get 25 feet cubed per minute. Alright, we have a 5 feet squared, so that's going to be 25 feet squared. times dr dt. All right, and now we can see that both sides have a 25, so that cancels. It's going to leave a 1. All right, so let's flip dr dt. Let's flip this equation around. Dr dt, and then feet squared and feet cubed. So if we divide both sides by feet squared, we're going to just be left with feet. All right, and then since the 25 is canceled, it's 1 foot per minute. So the balloon's radius is increasing at 1 foot per minute when the radius is 5 feet. That's the answer.